morning. Question on the board is for polar equation. We're gonna convert the polar equation to a rectangular equation. Maybe we did a little too fast last time we were converting the equations. If we want to convert the rectangular equation, what we do is replacing x by r times cosine theta, replacing the y by r times sine theta. So that's how you convert from rectangular equation to polar equation. But then you can convert back and forth. So if you have a polar equation, probably convert it to rectangular equation. You have to look for substitution tool, like ways to substitute the equation. Like this one, we have sine and cosine in the equation, so we can try to see if we can create x and y from the polar equation. Okay, so let's review what was the main idea in the conversion. Is to keep in mind the conversion formula. One says x is equal to, maybe I should make it x equal to r times cosine theta. That's, and then y equal to r times sine. We use theta. I've said theta on the keyboard, so let's try to draw the letter theta, big letter theta. So that's how you convert from r times cosine to x, from r times sine to y. Now you can see this equation does not have r times sine or r times cosine. But what if you only have sine? Okay, and then there are two ways to do this. For example, we have sine in here, but you have to have r times sine create a y. So one of them is think of sine as y divided by r. But then you have this extra burden to get rid of the r. So normally we don't do it that way. Normally we would, first we want to convert the equation. First you take that equation that's already in here. Very simplify. So to begin with, this equation has r equal to formula of theta. It's not the simplest form. Now when there's division, I would try to multiply both sides of the equation by the denominator. So if you do that, this equation becomes this. So we multiply both sides of the equation by, okay, we multiply by the denominator. So the 2 sine plus 4 sine is multiplied. And so if you multiply both sides by that, you have r times 2 times sine theta plus 4 times cosine theta. And this is equal to 5. So that we get to remove the division relation and replace it by multiplication relation. Still, there's supposed to be theta. That was okay. Are we okay so far with the conversion? Right? Okay, so these two equations are equivalent. One is represented by division, the other one is represented by multiplication. They're essentially the same equation, but then you can see we get to multiply r with sine or cosine. So if you distribute the r, then you have 2r sine theta plus 4, and then you have the r multiplied in as 4 times r cosine theta. And that equal to 5. So what we are doing here is trying to multiply the r into the whole thing. And then that was supposed to be theta. Okay, so then you can immediately see that we have r times sine theta, we have r times cosine theta. So this is the part that's slightly difficult, more difficult to convert from polar to rectangular equation because you have to balance the r and theta has to be converted simultaneously to either x or y. But now we can see those. So the r times cosine b will be replaced by x, and the r times sine will be replaced by y. So this is essentially 2 times y, and that's essentially 4 times x. So you have 2 times y plus 4 times x equal 5, and you can see what kind of equation it is. You can see that it's actually equation of line. So the polar version of equation of line is different than the rectangular version of line. These are all lines, and that one obviously would be wrong. So try to choose out of the A, B, D, choose the right one after the substitution. That can explain this type of question. And then we should also start seeing some pattern. Whenever next time we see a polar equation like that, we would know that that's actually a line. Equation of a line. So we're quite familiar with equation of line in the rectangular form. Whenever the variable is equal to 1, we know that is a line. But then in polar form, it's not that visual and determining from the degree of the equation to tell whether that's a line. We have to look for a pattern. If you haven't submitted your answer yet, feel free to ask questions. In the online classroom, are you missing? Okay. They might be overdue. I can reopen them because chapter 8 after test 3 they're due. But I reopened 9.2, so you should be able to open 9.2. All the past homework that's already due, I'll reopen them this month because it's the end of semester. I would reopen all the past homework for preparation for final exam. So you don't have to worry, that they should be opened soon. Any other questions? Anyone need the link if you're in the online classroom? You see more and more people choose to attend online. Question. You need the link, right? You need the Blinker link menu. Let me go back there and find the thing. Right. Oh, you have it. Okay. Yeah, you have it. You should be able to click on the answer. The answer is right. So we substitute r times cosine for x. So that's really 2 times y plus 4x equal to 5, because x times cosine is r times cosine is x, and then r times sine is y. That's really y. So the equation should be 2y plus 4x equal to 5. So the answer should be D. Anyone else that haven't submitted yet? Sorry, I should really pay more attention. We'll go to the side. Okay. Right. That would be the attendance for today. Oh, the answer is D. Have I not mentioned it? It's 2y plus 4x equal to 5. That was a conversion equation. This is how to convert from equation to this. And applying the conversion equation, we realize it's this, so it's D. And you hadn't choose the right answer yet. Hayden, are you not online? It's D, as in the last one, number 4. Any homework questions? Any homework question from what work? Okay.
I think number C probably.
I'm going for number 6. All the homework for chapter 9 is open. Feel free to ask questions as you see a part question. 9.4, number 6. This one, which one?
I'm just wait. I'm confused. Again, about how to get the whatever it's called, the angle.
Okay, I see. So let's start from the beginning. You have a point that's in the polar form, which really means the distance is 3 and the angle is 0.
Yeah.
So you can pretty much mark out because the angle is 0, it's on the x-axis, positive x-axis. It's essentially 3, 0 for rectangular coordinate also. So we can draw that point, and then this is A, which is about this representation. All right, so if we draw this point, it would be radius 3, angle 0 is here. Angle and this distance is 3. This is we're trying to look for another parabola point for this point. As we mentioned, rectangular coordinate are unique, but rectangular coordinate is not. Rectangular is unique. Polar coordinate is not unique. That's why we can have other ways to represent the same point. Here it says this is giving us a clue because there's really many of the same points, many representations. It says we want the R to be positive and we want the angle to be larger. Right, so basically you can see the radius it's already positive, so radius equals 3 if you are allowing for a positive radius. So according to the requirement, this is definitely just 3. The original one is positive, and all we have to do is turn the angle. The reason that we have multiple representation is because this whole thing can rotate. So we make the angle bigger. This is really making it bigger, right? Originally it was 0, so you add 2 pi to it. So the angle here would be 2 pi.
I got the first one. It
Okay.
was like when like it's a negative pi to 7, not 7,
Okay.
negative pi over 7.
That's the one. All right, I'm trying to explain the pattern. So basically, if you want a positive radius, then all you have to do is minus or plus 2 pi to your angle. That's what we did. We take the 0 and add 2 pi because we're allowed to make the angle bigger. Now, the second question is now we want the radius to be negative. The only possible radius for it to be negative is the opposite. So that would be the -3. And then if you change the angle to change the radius to negative, then the angle has to be the opposite, which is 180 degree bigger or 180 degree smaller. In this case, because the angle is required to be between 0 and 2 pi, we have to make it bigger. So the angle here will be a 1 pi. There. So basically, if you do not change your radius, all right, then you can change your angle by 2 pi. You can add 2 pi or minus 2 pi because 2 pi is a revolution. That means you turn all the way back up to the same direction. So that's 2 pi. All right, so this is when you do not change your radius. Now, if you change your radius to the opposite, so instead of going this way 3 steps, and we would go that way, so you have to have 180 degree to the original angle. So if you change your radius to a negative, then your angle has to add or subtract 1 pi. It depends on whether you're allowed to go big or small on the angle. So there's many answers to it. So you can even combine. So if you want the main angle, like if we want the angle to be bigger, we can also add 2 pi to this. So it can be -3 and pi, -3 pi, or -3 5 pi. So there actually, that's the reason there's many answer to the angle because the revolution. All right, so essentially this is how we answer the first question. And that's -3, and that's gonna be 1 pi. And then, you said most likely the bottom one or bottom two?
Yeah.
Okay, so maybe we'll start with B as well. For B. So we can detect some pattern and then it's easy to follow. So find another parabola point, and this time we make the angle bigger and then the radius is positive. So for the first question, we follow the same reasoning. Since we are allowing to have positive radius, the original radius is positive, so that won't change. Okay, so then the one that we are changing is the angle, and here we're making the angle bigger, so we add 2 pi. So you take the original -pi/7, at least that's what I'm mine, plus 2 pi, and that will be moving the angle bigger, but you don't have to change the radius.
But when it's big enough for to be within the bounds it gives us, because it has to be from 2 pi. to 3 pi.
Right, so we should add 4 pi. Yes, you're right, yes. We have to add or -2 pi until we're reaching the right boundary. The second question, the radius is negative, so we have -2. Then the angle is smaller, so this time we will have -pi/7. If you want to make the radius negative, you have to either plus pi or minus pi. In this case, the angle is set between 0 and -2 pi. We have to minus pi because we were required to move the angle to that range. Are we okay? So the last one, and find another parabola for this, for the R to be positive. It was originally negative to be positive. It has to be +1. Now they are opposite. If the radius become the opposite, then your angle has to be add or -1 pi, right? But if you switch the sign, you have to have a 180-degree difference in angle. If you keep the same sign for your radius, then it should be the same angle. But if you want to move it, you have to move it at a 2 pi distance. Hope that kind of makes sense. All right, so then we're gonna add, this is bigger. So we add a pi, it was originally -pi/2. It was negative, we have to make it bigger. If we add pi, that's
Not big enough.
that's not big enough. So we have to add another 2 pi, just so it's in the right range. So if you only want to add 1 pi, it made it the right point, but now the right range for the angle for that. Another 2 pi. Add the first pi to make sure that the radius change match the point. Add a second 2 pi just so the angle will be in the right range. Are we okay? Any question? The next question, find another pair of point that R will be negative. It was originally negative, so we put -1. And this time, you see, we are keeping the same radius. Therefore, the angle should be like in 2 pi distance from the original angle. And we want it to be between 0 and 2 pi. All we have to do is add 2 pi. So -pi/2 plus 2 pi would be sufficient. Were you able to answer your question?
Yes, that makes so much more sense now. Like, do I just stab in the dark and give the answer?
But normally is after you have already thought about it, then the explanation will make sense. If you just start new, maybe it was a little too fast, I'm not sure. So it depends. Any other questions from the homework? As you go through the homework, try to think about a reasoning or understanding. If you really are stuck, then we can talk about, then we can discuss the solution. So then we can try to figure out if there's any pattern, any rules, any method that kind of make it easy. So any shortcut will not be a shortcut unless you actually had searched a little bit. Yeah, you struggle with it a little bit. Okay. If you're in the online, yeah, okay. I was gonna open it by the end of semester, but yeah, I can open it now. Let's see. I hope to open 8.5 and you 8.6. You change the date. Right, let me have it open to the 9th for this month. See if you can finish before the 9th. Is that okay? Any other homework questions? All right, if not, then continue where we left, Thursday. We're gonna talk about polar calculus with polar equations. Right, last time we only started with the derivative and the tangent when we have a polar equation. Okay, so we started by converting the polar equation. This is a polar equation. The polar equation normally is representing radius with a function of theta. So you can think of, most of the time, we think of polar equation as angle being the independent variable, radius being the dependent variable, but it could change. So if you do have a radius formula, let's call that f of theta, then because x equal to r times cosine, y equal to r sine theta, this is a by nature relation between x and y and r and theta. So we replace the r, which originally could be a number, now we replace it by a function. So x equal to f of theta, you can also call that r theta cosine theta, and y equal to r theta sine theta. So now you have multiplication for x and y, and the formula for x and y, that becomes a parametric equation, right? Polar equation look like this, the parametric equation looks like this. We'll try to connect them, so the method that we're using for parametric equation now works also polar equation. So based on the 9.3, the calculus with parametric equation, we can find the derivative. So it's dy dx. You want to find derivative y with respect to variable x, then equal to the derivative of the y function divided by the derivative of the x function. To find that, you have to do product. That's why it looks a little bit complicated, but you can actually simplify your formula for x and y if it's possible. Then maybe the derivative can also be simplified, because essentially it's derivative of parametric equation. Find derivative y and find derivative x if they are there, if it's possible to simplify them. All right, so normally I would always find the y and x formula and then differentiate from there. So I follow the parametric differentiation instead of treating this as a schema. Because as a formula, this dy dx formula is lengthy and sometimes we might have a typo error as we're going through the process. So it's better to understand the reasoning than the formula itself. So we went through this one. It was a chromosome that have a little loop in the center. So there's quite a few vertical tangent line and horizontal tangent line. We spent quite some time last Thursday to figure out those points. The solution, the white dots and black dots are horizontal tangent line and vertical tangent line. The red line is a tangent line at the point power 4. And this will kind of look like the same line. Now, this question, it says find the equation line tangent to the graph at the pole. Polar equation, the word pole is the same thing as rectangular equation, the word origin. So pole essentially is the origin. And, I think there should be two tangent lines if we try to turn the equation tangent line. Okay, so visually, this is a sign. So sign is above the pole, the origin, so like this. With a little, because 2 is bigger than 1. So if you try to draw the tangent line at the origin, this is the origin. So you will see a tangent line that's in this direction, and then a tangent line in this direction. So there should be two tangent lines at the pole, at the origin. So how do we determine the tangent line? Number one, we know that this is when x equal to 0, y equals 0. So the point of tangency is simple enough. So if we're trying to determine a line that goes through the origin, all you have to do is to determine the slope. So anything that goes through 0 point, it's y equal to kx. So that's the equation. Maybe we use m, y equal to mx. N will be the slope. But remember, not in the past we will use y equal to mx plus b, right? M will be the slope, b will be the y-intercept. Because the line is going through 0, 0, so the b is equal to 0, right? So then there's we don't have to calculate the b because we know that it's already 0. And then what would be the m? M equal to tangent theta. Tangent theta. If you draw a line at the origin, that will be the theta. And that's the theta in the polar coordinate, the same theta that's in the polar coordinate. So if we solve the equation for the slope for this theta, then we take a tangent, that will be the m. So that's our plan. M equal to tangent theta, all we have to do is find out if theta equal to what at the origin. We want to find the derivative at the origin. So let's calculate the dy dx first. Dy dx is equal to according to what we said, it's supposed to be equal to the derivative of the y with respect to the parameter. Here we have a theta and the derivative of the x with respect to the theta. And then you might ask, what's x, what's y? In polar coordinate, the x is equal to r times theta, and then now it's r. So r times cosine theta is the x value. But this case, in our case, r is a function, so r equal to 1 plus 2 sine theta. And we're repeating what we were doing last Thursday as far as finding the derivative. So that's our x. And then y equal to r times sine theta. Let me try to type it in. So what's our r? R is 1 plus 2 sine theta. Right, that's r multiplied by sine theta. So this is 2 times sine theta, that was the r, and then this is sine theta. Okay, anyway, so this is looking like 1 times cosine, that was cosine theta. I'm supposed to find the derivative, so I'm trying to simplify the x and then simplify the y to get ready for the differentiation. That's going to be cosine theta plus 2 sine theta cosine theta. When you multiply all together, this is actually 2 sine, that's actually sine 2 theta. Sine of 2 theta, double angle formula. If you want to combine it, so it's easier for differentiation. The bottom one is 1 times sine is sine theta. And then 2 sine theta times sine theta is 2 sine squared theta, 2 times sine squared theta. So there, we try to multiply r with cosine, or multiply r with sine, so we simplify them. Whatever you know that you have to find the derivative down the way, it's better to simplify it before you have to find the derivative. So that's simple enough. Let's try to think about the differentiation process. So we done here, we have to find the derivative of y. This is our y. Derivative of sine is cosine. Here's just going to be cosine theta, which is the derivative of sine, and then 2 sine squared theta. Derivative will be 4 sine theta. And then that's power 2, and you have to do chain rule. So derivative sine is cosine theta. So that will be the derivative for the y function. So that's the derivative of this term. Any question? So this power rule for the 4 sine, this function, they're the power 2, so move the power to the front. But then after you differentiate the power 2, you have to differentiate the sine, the sine is cosine. So you have to multiply this part, pretty much power rule and chain rule. Okay, so we divide this by the derivative x function. So here's our x function. And we have to differentiate the cosine, which is negative sine. Negative sine theta is the derivative cosine, and then derivative sine is cosine, so plus cosine 2 theta. And then we have to multiply by 2, because there's 2 theta inside of, according to chain rule. You have to multiply by 2. So this is cosine 2 theta. That's the derivative of sine 2 theta. Derivative of sine 2 theta is cosine 2 theta times 2, because the derivative of 2 theta is chain. Any question? All right. So we need to know the value of it. And then first what we'll do is figure out what theta is supposed to be. When x equal to 0, y equal to 0, there's both of these equal to 0. So we have to find appropriate theta. See, we try to find m tangent theta, which is the slope, right? Right? So you have to know the right theta. If the y equal to 0, maybe theta equal to 0. And then if theta equal to 0, that's 0, but cosine theta is 1. So the angle, you can see the angle here, right? The theta, it doesn't look like it's 0 degree. Yes. Right, so we want to try to figure out a number that will make the x equal to 0 and the y equal to 0. So we go through this one. So it looks like a 0 is not good. To make it equal to 0, so we can't make theta equal to 0. Let's solve this point. I'm running out. So let's go by this. Y equal to 0. So this equal to 0. Right? And then that means the sine theta times 1 plus 2 sine theta equal to 0. And factor this so we can separate them. Okay, we factor them, and then we can see with 2 factor, it's easier to solve the 0. You set sine theta equal to 0, which theta equal to 0, and we already know theta equal to 0 is not the answer. Because if theta equal to 0, x is not 0. We want x and y both equal to 0. So that did not work. So we're going to choose the second factor, the 1 plus 2 sine theta equal to 0. And we solve that one. You would have 1 plus 2 sine theta equal to 0. And then the sine theta equal to negative 1/2. Sine theta equal to negative 1/2. And then we can solve the theta. Theta will equal to sine inverse of negative 1/2. Sine inverse of negative 1/2. We can use our calculator, and what kind of angle have a sine negative 1/2? It's sine inverse gives you a negative angle. This is actually negative 30 degree. Is that true? The way I draw it is not exactly right. Let me try to confirm the angle.
130.
Okay, so the 30-degree is fine? I mean, maybe that's this one, the negative 30 degrees. But we normally would prefer it to be a positive angle, but let's calculate it. There's two of them. We can find one and then work out the other one by symmetry. Let's calculate this. So we'll use negative 30 degree, or you can call that negative pi over 6. So, but by the understanding of the graph, we know there are two tangent lines, and if we find one, we know we will find the other one. That one looks like negative. So I think that will be this line. We plug in theta equal to negative pi over 6 to the calculation over here to get the m calculated. Or you can just find the tangent, right? We can calculate this using the derivative. The derivative will give us the slope of the tangent line, right? Are we okay? So I feel like maybe there are two ways to do this. I already kind of see if we plug in theta equal to negative pi over 6, it's negative root 3 over 3. That's the slope of the tangent line. Or you can plug in over here. Plug in the theta equal to negative pi over 6 cosine negative pi over 6 plus 4 sine negative pi over 6 and cosine and so on. So this calculation using the dy dx, you can calculate the slope. Using the tangent theta, you can also calculate the slope. But this is definitely easier. I wonder if the answer will be the same. We can double check if you plug in the tangent theta. When theta equal to negative pi over 6, it's negative root 3 over 3. Okay, and then you go back to the line that y equal to negative root 3 over 3 x. So that's one way, seems to be a shorter method. You can also put in the derivative function for dy dx. That also allows you to calculate the tangent, the slope value, but you have to plug in theta. So we have cosine negative pi over 6 in here, which will give you negative root 3 over 2 plus 4 times negative 1/2. That would be the sine value. And cosine value is negative root 3 over 2. The cosine is negative. The sine cosine should be positive. Cosine negative pi over 6 is positive. Root 3 over 2. That's positive. The sine is negative. Cosine is positive in fourth quadrant. So down this is a negative 1/2, which is positive 1/2. That theta is the theta sine negative pi over 6 is positive 1/2 plus this is a cosine 2 times negative pi over 6 is cosine pi over 3. That's 1/2 times 2. So this is actually 1. 1 plus 1/2 is 3/2. So in the denominator, we have denominator is 3/2. Numerator is this negative root 3, right? 4 times negative 1/2 is negative 2. Negative 2 times root 3 over 2 is negative root 3. Negative root 3 plus root 3 over 2 is negative root 3 over 2. To simplify the 1/2, we have the same thing as negative root 3 over 3. And that's the slope of the tangent line. We can confirm this by a graphing of what we have. The polar equation is r is equal to 1 plus 2 times sine theta. So that's the graph. And the line that we're talking about is what for negative square root 3 over 3. That's the tangent of negative pi over 6 times x. So that's that tangent line. The other one is symmetry, is y equal to positive square root 3 over 3 times x by symmetry. We can zoom in to see if it's truly tangent, right? Tangent line. You can see the angle is negative 5/6. Any question? Yes,
So find our point, like -5/6. Why did we choose y again?
we can use both. You can also set x equal to 0. You can set this equal to 0, but it's simply easier to solve the y. See, y has sine theta and sine theta. So you can factor the sine theta and solve for a solution. But if you set this equal to 0, that also works. It will have both sine theta equal to 0 or 1 plus 2 sine theta. So there is a factored form. So if you want to set x equal to 0, also it's essentially, we're just trying every possible equation that involves theta that allows us to figure out theta equals. So we just need an equation that has theta. X or y variables. Any other question? Yes. So this is another equation. If you look for more organized solution, I have to say I'm pretty much using the whole board as my scratch paper is a bit messy. You're welcome to look through the textbook. Once you understand the process, we can definitely organize the layout to make it look better. That would be how we determine equation of tangent line. All right, now we should also be able to calculate area involved polar form, and we talked about the formula last Thursday before the class is over. Being able to calculate area is one of the main things that integration can do, calculus can do. So when you are learning calculus, there are two of the most popular questions, which was the geometry question, calculation of the area, calculation of volume. These are the two things that you can't really completely avoid. But even with calculation of volume or area, it depends on what was the given equation. Is the equation given the rectangular form, parametric form, or polar form? Depending on what is the information being offered, the method for solving the area is different. Okay, so how do we calculate area if you have rectangular equation? The nature of rectangular equation is we are using vertical distance and horizontal distance as a way to locate or understand shape. And that also means you can divide up your entire picture into a lot of squares. And that's why, depending on how, if you see something like this, all right, when you try to figure out how large the area is, you think of it from left to right, bottom to up, and that's how we look at things, and which causes the way we calculate. Even with numerical method, you can do it this way. You can have horizontal slices of things, and then you can have a vertical slice of things. If you're careful enough to look at the area of each individual pieces, you can start counting how many small pieces in there, add it all together to get your total area, right? So look at it is, if you want to find the size of the occupied area, you look at it from pretty much a rectangular point of view, the way to think of it. All right, if we have the equation that's offered in the polar form already have angle in mind. So you have the rotation of it's already in the original thinking. So your curve sum from here and 0, and then a little bit bigger. That's like 15, 30, 45, and then 60, 65 maybe, and then 90 degrees. So you have the angle slowly changing. As the angle change, the distance from the point to the origin is changing. And then we model that change with the formula f of theta. So f of theta is giving you the distance using theta as an input. As the theta change, the radius is changing. So that means if you have an area calculation that's more angle oriented or revolution involved in the setup, then polar calculation will be better. If you have an area calculation that has a very well defined left and right, bottom and up, so if the boundary is well defined in the rectangular format, then the normal Riemann area or the numerical slice, horizontal vertical slice, will be a better way of trying to find approximately what was the area within the region. All right, so we talk about the formula here. The area calculation using polar format is A equal to 1/2 integration of r squared times theta. The reason for this is you can slice up the area into small parts. And this is a thing about the area calculation. So this, I'm explaining this just so the formula is a little easier to understand. So let's think about try to calculate like this part. So basically, when the angle is really, really small, like this, when the angle is small, you're like, how large is this little piece? Okay? If the angle is small, then you, when this is the angle, let's call that d theta. So your central angle is a really small angle, and that's why the whole thing looks like a really thin slice of a triangle. The area for the triangle is 1/2 base times the height. Now, what would be the height of the triangle? You can draw a perpendicular line to the base. This part is your base. This part is the height. The height is supposed to be at the center, but if the angle is really, really small, you can think of the whole thing as consistently the same, right? So the curve will be not that curvy if the theta is super, super small. That's why we can think of it as a triangle instead of at the section of the circle. So in that case, the h essentially is the radius. And then about the b, b is part of the arc. Okay? Our arc is a slice of the entire circle, and the length of the arc can be calculated by r times theta. Because the entire circumference, if you have a big circle, the entire circumference is 2 pi. So circumference is measured by 2 pi r, meaning it's essentially r times the angle for the whole circle. That kind of gives us the idea that the length of the arc depends on the center of the angle. The smaller the angle, the smaller the arc. So you will have a big arc if the radius is large. You will have a big arc if the theta is large, and they're essentially proportional. So radius times the central angle gives that distance. And this is really how the reason we define reading measure. Reading measure for the theta is the arc distance and the radius. Okay, so mean that if the radius equal to 1, the arc equal to the theta. That's why if you multiply r by the angle, that's your arc. So we have a b, which is r times theta, and the h is r. So this is essentially 1/2 r times theta times r. Notice the theta there is actually d theta. It's really, really small slice of the theta. So if you have a really small area that you need to calculate this part, dA actually equal to 1/2 r squared times d theta. So we write that as d theta instead of theta. We write that as dA instead of a, because we're talking about only a very small part of the entire area. To calculate the whole area, you have to add it all together or combine them. So we have to do the integration. So the integration of dA give you the actual a. I mean, a and dA, the differences is dA is approximation of a really small part of the entire area. All the dA has to be added together to give you actual a. But we often analyze the dA in the calculation step, so we can have a better formula for the multiplication. This is the formula for dA. Just like before, we have the ds. Remember, ds was the square root of f prime squared plus d prime squared. Also, sorry, the derivative of the x and y, and then dt. So just want to review this formula so we kind of see why the formula for the area on the arc in a polar form is giving that this formula. Sure, we got time. Okay, so let's look at the equation. It says we want to find the area of the circle defined by r equal to cosine theta. Because it's a circle, we actually has an easy way for the calculation. Area for the circle is pi r squared. If we have the r, which is the radius, we will be able to calculate area a lot faster. But here we're trying to review and confirm the formula, so we're gonna do this as a little exercise for the area calculation. And then we're gonna then confirm the perception from geometry. Right, according to our formula, area in the polar form is equal to integration of 1/2 r squared d theta. Area is a two-dimensional calculation. R is one-dimensional, so r squared is two-dimensional. If you wonder what happened to the theta, theta is essentially a ratio between it's a ratio between the radius and it's a ratio between the arc and the radius. So we angle does not happen. This is equal to so this is a entire circle, so theta should go from 0 to 2. Right? 0 to 2 pi. Think about if the way to the theta, we have to find out initial value for theta and terminal value for theta. So 0 to 2 pi. All right, so here remember the r is a function. Theta is not a number, so it's actually 0 to 2 pi 1/2 cosine theta squared. That will be the computation. And then we can bring the 1/2 to the outside of integration. And that will be 0 to 2 pi cosine squared theta. Theta. Do you still remember how do we integrate cosine squared theta? What was the antiderivative? Do you remember how do we integrate cosine to the power 1? Which is sine, right? Integration cosine d theta equal to sine theta.
Would you use that power reduction?
Right, power reduction formula. So if we have odd power, we can bring one of the square power to the side and then have that single power into a substitution method, right? With odd power cosine, we can do substitution. When we have even power, we have to do power reduction. So according to the power reduction formula, cosine squared theta equal to, let me write down the formula first. So in the power reduction formula, cosine squared theta is equal to 1/2 plus 1/2 cosine 2 theta. Right, if you write it this way, then there's square on the left, there's no more square on the right. We will reduce the power by 1/2. That's why it's called a power reduction formula. So according to this formula, this is equal to 1/2 0 to 2 pi. And this is going to be 1/2 plus 1/2 cosine 2 theta. So after we reduce the power, we can then integrate it. So it's going to be 1/2. If you integrate the 1/2, you get 1/2 theta. This is 1/2 d theta. 1/2 theta. And if you integrate 1/2 cosine theta, antiderivative cosine is sine, so it's 1/2 sine 2 theta. But this is the integration of 2 theta according to the reverse chain rule. You have to have a 1/2. And that will be the entire antiderivative is calculated as 0 and 2. Any question for the integration parts? You can think of this does what happens with coefficient, but when you try to find the derivative sign, is cosine, but then you also have to multiply by 2, right? That 2 will be canceled by the 1/2, therefore there's no, so that will be the derivative that will be there. So you're gonna plug in 0 and 2 pi. After we plug in 0 and 2 pi, you see if you make theta equal to 2 pi, sine 2 theta would be sine 4 pi, sine 4 pi equals 0. If you make theta equal to 0, sine 2 theta will be sine 0, sine 0 also equals 0. So no matter which point, 2 pi or 0, this will equal to 0. So the final answer will be the non-zero part will be this part. So we have to plug in 2 pi for theta, and we have 1 half times 1 half is 1/4 times theta. Theta is 2 pi. So the answer is pi over 2. Any question? Wonder if that's right. Let's see, according to geometry, this is a radius 1/2 circle. The area for a circle is pi r squared, pi r squared. So that will be pi times 1/2 squared. So it should be pi over 4. I must have the integration boundary wrong. It's 0 to pi. So this should be integrated 0 to pi, 0 to pi. So that should be 1 pi. We can draw the circle to determine the integration boundary, and then the final answer will be pi. I know for sure that should be the right area. So let's look at the circle represented by graph. R equal to cosine theta. You can see, let's zoom out. You can see if you set 0 to pi, that's already the whole circle. So we should have 0 to pi. The revolution repeats. So if you have this pi equals 0 to pi over 45 degrees, if you have pi over 2, that's half circle. And then if you have 3 pi over 2, it's already a full circle. So this pi over 2 is a little too large. Pi will be. Are we okay? Because it's a revolution, you can also trace it little by little. And when theta equal to 0 is over here, and then when theta equal to 45 degrees, it's over here. When theta equal to pi over 4, cosine pi over 4, cosine pi over 2, cosine pi over 2 equal to 0. So it will reach half circle at pi over 2 already. So 3 pi over 4 will go here, and then cosine pi is already back here. So we don't have to integrate from 0 to 2 pi, we integrate from 0 to pi, that would be sufficient. So we would end up have to calculate it twice if we do a bigger angle. So the angle 0 to 2 pi, the terminal point is too large. Any question? So this is the polar coordinate. We kind of have to identify the end point to make sure it's only going through one circle instead of 2 circles. All right, this is calculating the area of the cardioid R equal to cosine theta, bound between theta equal to pi over 6 and theta equal to pi over 3, as shown in this figure. Is it not in here? I'll draw the picture myself. All right, so we have R equal to 1 plus cosine theta. Okay, so that's a cardioid between pi over 6 pi over 3. All right, so pi over 6 and then pi over 3. Okay, and then let's draw those two lines to make. We want to find the area, so let's try to have the edge of the area. One is y equal tangent pi over 6. Trying to draw the line. that line, and then we have x is between 0 and the other end. Right? 2. Well, we might have to calculate the radius from the formula. It's essentially 1 plus cosine pi over 6. With the radius is it up? Okay, the other boundary, I was gonna try to open another line, y equal to tangent of pi over 3. And this also, let's try to limit the x value. So the 1 plus cosine would be the boundary of the one. Isn't that supposed to be the one? You said 1/2?
It'd be 1.5.
Why?
1 plus cosine.
1.5, yes. Right, it's a little large, for the weird. Right, it should follow the formula. I would think it would follow the arm, you put 1 plus cosine theta, right? It was right between pi over 6 and pi over 3. We're trying to find area in this region, so I'm trying to put a boundary to the region. Are we okay there? So it was like, that's pi over 6, that's pi over 3. So we find the area within this curve between these two. So this will be the lower boundary, this will be the upper boundary for the integration. But somehow that doesn't work here. Right, the radius is supposed to be right. Oh, it's the R, it's not the X, right? I think X value. So the X value is this.
Yes.
This is the X value. So we want to put the X value up. We have to take the R and multiply by the cosine. The cosine of the angle is where the X value is supposed to be y over 3. That's the X part. Yeah, so same thing over here. This is calculation of the R. We're trying to put the boundary for the X, so it's multiplying by the cosine pi over 6. That is the appropriate boundary. That way the shaded part will be perfect. So anyway, I'll just play with the picture there, but the calculation is well defined because we have the R, we also have the integration boundary for theta. So we follow that definition. So the calculation for the area is A equal to integration of pi over 6 to pi over 3. Supposed to be 1/2 the R squared d theta. The R is 1 plus cosine theta. R squared d theta. So remember, this is A equal to integration 1/2 R squared theta. That's the formula we're following. And here we're calculation. Any questions? All right, so the rest is all about the algebra. So we expand from here is equal to 1/2 integration. We're calling algebra in this part. We don't have to put any integration limit until the last evaluation part. So square this, we have 1 plus 2 cosine theta, and then plus cosine theta squared. And then d theta. So you can see that as we're doing more and more full exercise, we have to review our skill on how to handle trig integration. All right, so again, this part you have to integrate the cosine square, and then we have to do a power reduction formula. So do it one more time. We'll have this is equal to 1/2 on the outside integration 1 plus 2 cosine theta. 2 cosine theta plus this cosine square is 1/2 plus 1/2 cosine double angle cosine 2 theta. That one equal to this. They're essentially the same thing. And now once they are all ready, so now we can find antiderivative. If you want, you can combine the 1/2 with 1. These two combine. So the calculation will be 1/2. The 1 plus 1/2 is 3/2. But if you integrate 3/2, you get 3/2 theta. Okay. Integration, the 2 cosine will have plus 2 sine theta. That's the antiderivative for the 2 cosine. And then we find the antiderivative for the 1/2 cosine 2 theta. It will be 1/2 sine 2 theta. You also have to divide another 1/2, so it's easier just go 1/4 sine 2 theta. All right, that finished the antiderivative. Any question? So now we're gonna put in the theta. Theta is from pi over 3 to pi over 6. Okay, this is equal to 1 by 1. I feel like that's a lot of value. 1/2, 3/2 theta. Let's say theta equal to pi over 3 plus 2 times sine 3 theta. Sine 3 theta is root 3 over 2. So root 3 over 2 times 2, that's root 3 plus 1/4 sine 2 theta. Theta is pi over 3. 2 theta is 2 pi over 3. Sine 2 pi over 3 is equal to somehow. See, this is 1 over 4. So this is going to be 3 over 2. Okay, so that's the upper limit value, and then we're going to minus the lower limit value. We put in pi over 6, so 3 over 2 pi over 6 plus sine pi over 6 is 1/2. 2 times 1/2 is 1. And then we have 1/4 sine 2 theta, 2 pi over, so sine pi over 3. That's still 3 over 2. Okay. Now it's time to do subtraction. Let's see, the whole term can be canceled. This one is equal to this one, so they cancel, subtract out. The rest, I don't see opportunity to cancel them out. This cancel the 3. This cancel this, we have a 2. So 1/2 pi over 2 in here. And this is 1/2, that's pi over 8. Minus pi over 8. And then the 3 is plus 3 over 2. That's this one and this one. And then minus 1. 1/2. 1/2 times 1. This 1/2 times that one is actually. That's all. Yeah, 4 terms. Maybe we can combine the pi, right? 4 pi, pi over 4 minus pi over 8 is pi over 8. So that's pi over 8 plus root 3 minus 1 over 2. This is irrational. Root 3 is irrational, so we can't really combine them unless we put in a calculator and find the numerics. So that's pi over 8. We also have pi over 8. 4 root 3 over 8, that's root 3 over 2. So minus 1. Yeah, so I think it's a minus 1 half. So, okay. Yeah, I think just different representation of the same thing. The final answer should. Any question? So the computation may take some time, but the method itself is follow the law. Okay. Sometimes the area calculation might involve an outside boundary and the inner boundary for the polar curve. So you have R1, that's equal to F1 theta, R2 equal to F2 theta. We're assuming that one is bigger than the other one. So we're saying the area is bounded by an outer radius and inner radius, R1 and R2. And then the theta is bounded by alpha and beta. So initial angle and terminal angle is alpha and beta. And then the radius, a bigger one and the small one. I think we're assuming that R2 is a bigger radius, R1 is small. So that kind of like a ring, you have a center circle, outside circle, so outside minus inside. So then R2 squared minus R1 squared is how we calculate the radius. Any question? That's when you have a polar curve that has a hole in the middle. So this is the graphics. This is the R2, and then red curve is R1, blue curve is R2. And we have an angle alpha and angle theta being the boundary. So the region, the shaded region here have an initial angle and terminal angle, have the inner radius and outer radius. You take outer radius square minus inner radius square, and then you take it. Any question? So this is the example of applying that. Okay. So one of the difficulty in this kind of question is we are assuming that we have that alpha and beta, that's the initial angle and terminal angle, but when you actually look at a question, the angle is not given. So here we have a cardioid, that's the red curve, 1 plus cosine theta, this one. And then we have a circle, that's r equal to 3 cosine theta. That is a circle with diameter 3. 3 is the diameter of the circle. So this is bigger, as far as the region, but they have the intersecting point. So we want to find the area bounded by the two curves. So that would be the shaded area. That Any questions so far? All right. Now that we look at polar curve or area involved polar curve, one thing we should remember is that if you can try to graph it before you do the calculation, like this one, after you graph it, you realize that it can be half. If you can find the upper half and time to will be the lower half. I see this because you see the upper one from angle 0 to angle that one, right? What about the bottom one? This is, if you want to move over, this is a 2 pi, right? Or unless you want to accept negative angle, that will be a negative angle to positive this angle by symmetry. So the angle and the terminal angle and they're symmetrical about the x-axis. So unless we apply negative angle with usual 0 to 2 pi angle, it might not work. So okay, another burden of this kind of question will be identifying the angle. See the picture, the intersection angle is not given. So finding intersection point for any curve is the same. You pair the equation and then you set them equal. So how do we, I guess we won't be able to finish the entire question. At least we learn a little exercise on determining the intersection. So if we want to find the intersection, which is right here, that one and this one. Realize we're solving for two intersections, but then you can focus on the positive one. Again, because there's symmetry, this angle is symmetric with this angle. Right, the two angle, you don't have to find both. Find one, the other one is like negative or opposite of the other angle here. So we would set them equal. You set the this one equal to this one because this radius is the same as this radius at the intersection. They're not routinely equal to each other. But when the curves are intersecting, they would have the same R and same theta. So we pair these two equal to each other, then you have 1 plus cosine theta equal to 3 cosine theta. If we subtract the cosine, you have 1 equal to 2 cosine theta. And then you're gonna have cosine theta equal to 1/2. And we want to find one solution. We have inverse cosine to find that theta. You do inverse cosine, so theta equal to cosine inverse of 1/2. If you set your calculator in degree mode, cosine inverse of 1/2 is 60 degrees. Go ahead. Okay. So now we know a 60 degree also is pi over 3. And really measure. So we know this is pi over 3. This is the negative pi over 3. So the actual calculation will be 1/2. Remember that was polar area. 1/2 negative pi over 3 to positive pi over 3. Outer radius minus inner radius. This is the outside. This is the inside. So you have 3 cosine theta squared and minus 1 plus cosine theta squared. And then DC. That will be the calculation. That's it for today. We'll continue tomorrow. Thank you.
Can I take a photo of that? Thank you.